Welcome everyone. Today we're going to talk about quantum computing, an exciting new area of technology that could transform the way we solve problems. And don't worry if it sounds too complicated right now. I'll break everything down step by step so it's easy to follow and you can understand it. Let's start off with classical computing, which is what powers the devices we use every day. Classical computers run on bits, the smallest unit of data, which can be either a 0 or a 1. Bits control processing power, which determines how quickly tasks get done. But here's the catch. As problems get more complex, they take much longer and require more resources. Even though classical computers have advanced a lot, they still hit limitations when facing massive, complicated problems. That's where quantum computing comes in. Quantum computers don't use regular bits. Instead, they use qubits. A qubit can exist in multiple states at once, thanks to a principle called superposition. That means instead of being just a 0 or a 1, a qubit can be both at the same time. This unlocks incredible possibilities, letting quantum computers process information in ways classical machines can't. To visualize this, scientists often use something called the Bloch sphere, which slows all the possible states of a qubit. And don't worry if this sounds a little overwhelming right now. We'll get more into this in later videos. Superposition is one of the important concepts in quantum computing because qubits can exist in multiple states simultaneously. They can perform complex computations much more efficiently. Imagine flipping a coin when it's in the air. It's not just heads or tails, it's a mixture of both. That's how superposition works. Another way to picture this is with overlapping waves, where many possibilities are considered at once before the result is finalized. Now, another fascinating principle is called entanglement. When two qubits are entangled, the state of one instantly affects the other, even if they're far apart. This is different from anything in classical physics. In quantum computing, entanglement allows qubits to work together in powerful waves. It's especially important in secure communication, where entanglement particles can be used for encryption. That's nearly impossible to crack, because what you change in one can affect the other, and you have no idea what one change is. Entanglement is one of the keys to achieving what's called quantum supremacy, where quantum computers outperform classical ones. Basically, why would we choose quantum computers over classical ones? Now let's talk about interference. Quantum states behave like waves. And when these waves interact, they can either amplify each other, called constructive interference, or cancel each other out, called destructive interference. Quantum computers use interference to boost the probability of correct answers while canceling out wrong ones. This process is what makes them efficient at finding solutions. And again, we'll dive into this later on in other videos. For right now, this is all you need to know. When you combine superposition, entanglement, and interference, you get what's called quantum advantage. Unlike classical computers, which solves problems step by step, quantum computers can work in parallel, exploring many possibilities at once. This makes them incredibly fast for certain tasks. They can handle optimization problems, simulate complex systems, and even tackle cryptography challenges. Fields like pharmaceuticals and material sciences could benefit enormously from this speed. Because simulating molecules or designing new materials would take years on classical computers, but could be done much faster with quantum ones. These are the advantages of quantum computers and why we would choose a quantum computer over a classical computer. Moving on, where do we see this in the real world? Where are quantum computers used in the real world? So, here are a few examples. Drug discovery. Quantum computers can simulate molecular interactions in detail, helping scientists find new medicines faster. Another field is material science. They can model new materials for batteries, nanotechnology, or energy storage. This can significantly cause an increase in the economy for material sciences. Cryptography. Quantum technology can both challenge today's encryption and create new unbreakable encryption methods. And artificial intelligence. Quantum algorithms may significantly boost machine learning and problem solving. In short, quantum computers could transform industries from healthcare to finance to security. It's all over the place. Of course, it's not all solved yet. Quantum computing faces big challenges, experimental in nature. We're still in the early stages, and we're still testing theories and prototypes, but we're definitely making improvement towards the potential that quantum computing holds for us. In extreme conditions, quantum computers need environments like ultra-cold temperatures and high vacuum systems to operate. We'll discuss this later in other videos on why this is necessary for their functioning. And fragile qubits. Qubits are very sensitive, and even small disturbances can cause them to lose their state. This is why most quantum computers are found in specialized labs filled with cryogenic systems and shielding equipment. For now, they aren't practically used every day, but researchers are making progress. Instead of thinking of quantum computers as replacements for classical computers, the future will likely be hybrid systems. Classical computers will continue handling everyday tasks as this is vital for everyday functioning, while quantum processors tackle the most complex problems. This co-processing approaches combines the strengths of both systems, opening the doors for breakthroughs in AI, logistics, finance, and beyond. In fact, some companies are already experimenting with hybrid environments, showing us the direction this technology is heading. Moving on, the future of quantum computing is bright. Leading companies and research labs around the world are investing heavily in scaling up qubits, reducing errors, and building practical systems. With so much effort and innovation, it's only a matter of time before we start seeing real-world breakthroughs. We're living in a very exciting moment in technology history. So our key takeaways for today are classical computers, they use bits, but quantum computers use qubits. Superposition, entanglement, and interference make quantum computers unique. Quantum computing could revolutionize industries like healthcare, material science, AI, and security. But the technology is still experimental and faces big challenges. The future looks promising, especially with hybrid systems combining classical and quantum computing. That's the big picture of quantum computing for today. In our next video, we're going to be diving deeper into some of the most exciting developments in quantum technology and look at how scientists are turning these concepts into real machines. Stay tuned, it's only going to get more interesting and more fascinating. Make sure you do the problems at the end of the slideshow to test your knowledge on what you've learned today. See you next time.